Okay, welcome back. In this video, we are going to continue with optimization problems. And what we're going to go ahead and do is we're going to work on the surface area volume example, which deals with the liter oil can. So let's get started. It says to design a 1 liter oil can. Notice that 1 liter is 1,000 centimeters cubed. So that's already a restraint or a kind of a restriction that we have to make sure happens. This can has to contain 1,000 centimeters cubed of oil. It's going to be shaped like a right cylinder. All that means is that it's a cylinder that's sitting straight up. There are oblique cylinders which kind of slant. This one's just like a regular, I don't know, like a Pringles container. What dimensions will use the least material? So our answer is going to be dimensions, but for the least material. When I see least material, I start to think that's the stuff inside of the can is your volume. The stuff the can is made out of, that's your surface area. So I know that I have to minimize surface area. And it makes sense because if you're a person that's trying to sell something, you don't want to spend a lot of money on the material making the container. You want to minimize that cost, and one way to do it is to minimize the material used. And it says, what is the least amount of material needed to achieve this can? So the dimensions, and then, of course, the actual material that we're going to use. So we're going to draw a picture, make a cylinder, see how well I can do that with this technology. Then I will come down. So it's just a cylinder. The dimensions for a cylinder are going to be in terms of the height of the cylinder. So from the top to the bottom, that's your height. And then the radius is from the center of the cylinder out to the edge. That's your R. Since we are minimizing area, you can look up the surface area of a cylinder. But basically we're talking about, let's see, I'm just going to put A for area, is going to be 2 pi r squared, which is the top and the bottom. And then we have to add the lateral area, the side here, which is 2 pi rh. So what you're going to notice about this equation is, again, like the previous example about the river, we have two variables. We have an r here, and then we have an h. And we cannot have two variables. So that means we got to go back and find a secondary equation that allows us to replace those. We have one more piece of information we haven't used. The volume of this cylinder has to be 1,000 centimeters cubed. And you can look up the volume of a cylinder, but it's basically the area of the base, which happens to be a circle, times the height. So that's pi r squared times h has to equal 1,000 centimeters cubed. If we do that equation, I have a choice. I can either solve for r, which has a square on it, or h, which is all by itself. And you're going to see right away that it's easier to solve for the h. So I will divide by pi r squared. And then that should leave me h is equal to 1,000 divided by pi r squared. Because I know that h is equal to 1,000 divided by pi r squared, I can now come over here, and wherever I see an h, it would be nice to switch colors there. Wherever I see an h, I'm going to replace it with this quantity right here. So I'm going to do that, and then I'm going to simplify a little bit. I'm going to press pause and then come back in just a moment. So I've already replaced the h as I had talked about doing over here. And I put in my 1,000 pi over pi r squared. I'm just going to simplify, getting rid of the pi's, getting rid of the r's, or one of the r's on the bottom, and then multiplying the 2. I'm going to continue over here. So my area is going to be 2 pi r squared plus 2,000 over r. Keep in mind, 2,000 over r, keep in mind this whole thing is not a derivative. This is just the actual area, the surface area of the cylinder, but it's now in terms of r instead of r and h. Now we can take a derivative. This one's a little more complicated to do by hand. Not terribly, but we are going to set the second derivative equal to 0. And to do that, you can use your calculator. You can either put this area equation in y1, and then in y2, you can do the derivative. And remember how we pasted using vars, y vars, function y1. And then where it says x, you just put x. And our restriction is a little bit, how do I say? It's a little more complicated than the one before. But if you want to have a feasible domain, we're focusing on R. The smallest R can be a 0. Sorry, my pen's kind of choppy here. The smallest R can be a 0. And the biggest R can be would be if you extended R. Remember, keep in mind your volume has to be 1,000 centimeters cubed. If you extend R so far, H is going to continue to get smaller and smaller and basically disappear. And when you do that, instead of a cylinder, what you're going to have is a big circle. And so you're going to have pi r squared, that's the area of a circle, is going to equal 1,000. And that's a material we have to work with. So if you solve for r, you'll get that r is 1,000 divided by pi, and then you got to take the square root of that. And that comes out to about, it's 17 something, about 18. I'm just going to put about 18. So that means my answer is between 0 and 18. Again, that comes from either making r 0 or making r so big that h becomes 0, which in this case would make it a flat circle. So that would mean that pi r squared has to equal 1,000. Solving for r gives us the square root of 1,000 divided by pi. And the square root of that is 18. Alright, once you do that, you can graph this on your calculator. You can put the y2 in there. And then you can find the zeros. You can change your window for x min to be 0 and x max to be 18. That will bring everything to a nice, just a nice interval. Your answer is going to come out to 5.419. And then you have to run the first derivative test. But of course you have your calculator, so it should already be graphed for you. It goes from 0 to 18. And then here is our CP, 5.48 prime. And if you look at the graph of the derivative, you'll notice it goes from negative to positive, which goes down and then up. I can't show you that I don't have a graphing calculator, but if you just graph it like so, it should work nicely. And so let's go ahead and make sure we have the right answer. It says, what dimensions will use the least material? Well, we know our radius is going to be 5.419, and that's going to be in centimeters. So that means our height is going to be 1,000 divided by pi r squared. If you put that in a calculator, I believe it comes out to 10.8340 centimeters. And then the last question is, what is the actual material or the area, the surface area? And of course, you can either plug the r into the equation that only has r's, or you can put the r and the h into the one that had r and h. It doesn't really matter. I'm going to go ahead and pause and figure that out real quick and come back with an answer. Okay, so I typed this into a calculator, and if I did everything correctly, this is my surface area that I come up with. Okay, guys, hope that made sense, and we'll move on to the next one.